Okay, so let's continue. So the radioactive decay, there are two ways to use it. One is by default the analog mode. Analog means the normal way, let's say as close as possible as what is happening in nature. And there are still possible via UI command to somehow fine-tune the way to use this radioactive decay in practice. One is to enable or disable radioactive decay in various geometry volumes. So you can be interested only in one and you activate only in that region, in that volume, and on the other you disable, for instance. You can limit the nuclei in which radioactive decay can happen. This is useful if you are interested to one particular decay and not the full chain of decays. So you can specify via UI command which are the limits of the atomic number and the number of nucleons. In this way, you can select the one that you are interested. You can supply a user-defined radioactive decay data file for a given isotope. For instance, you are interested to one particular decay channel because you want to do some studies, or it's very rare, but it's a background, you want to study that one. You can provide your own file, or even the evaporation data file, which is used for this gamma emission. You can also, if you have some reason for not using the one of Geom 4, have your own data. Maybe you are coming from a laboratory where you may have precise measurement of a particular isotope, then you can specify that one. And you can also switch on or off, by default is on, the atomic relaxation, all this reshuffling of orbital electrons to get to the ground state. The other way to use radioactive decay, which is very useful in practice, is so-called bias mode, which means that you get a weight. There will be a lecture on biasing on Friday, so you will understand in more content. But essentially, it means that your simulation has some weight. It's not one, which is the analog normal life, but it will have some weight. And you have to carry this weight to get at the end correct results. And the advantage is that you converge to the solution quicker, spending less time, computing time, and you waiting for the computer using this biasing thing. For instance, you can set all the decay branch probability the same. And this way you will enhance the one which are quite rare if you are interested for some background studies. You can do splitting. That means instead, when you have a radioactive nuclei, instead of having one decay, you can split it in 10, and you have 10 decays, but then you have to take into account of overweight, which is typically 1/10 because you are oversampling. But so this is another trick to get more information quickly. Very useful is this activation thing. So you can specify, if you think about an accelerator, the profile where you have an activation, where your beam is hitting a certain target with a profile which goes even in months. And then you have another time profile, which is where you are interested to know the radioactivity, for instance. So imagine an accelerator beam, which is going on, and then you want to know in some part where some humans has to go and make some intervention, what is the profile as a function of the time of the radioactivity there. And here it is important, is bias, because it is not Monte Carlo, so we are not drawing a random number, doing all the details things. It's a kind of semi-classical results using this Bateman equation. So there is a way to solve this equation in an approximate way to get the results, this profile that you need in your specified window. And also you can also bias if you are looking to the decays only in particular angular region, for instance. You are not interested everywhere, but only in specific region. So these are all ways that you can speed up the result that you are needed, saving CPU cycles and also your time. But you need to keep in mind that there is a weight that you need to propagate in your plots, in your results, essentially. To use radioactive decay, there are two ways. One is, which is the best and simplest, to use one of the physics lists where radioactive decay is already activated. And if you take HP, any of the HP physics list or shielding, this is the case. Another one is that you take a physics list without radioactive decay, like FTFP, and with this one line of code, you use this, what is called physics list constructor on top of a physics list to enable radioactive decay, or you can go even in more detail, enabling, but this is something that we don't recommend, but it's possible to do this way as well. And there are many options that can be set via UI commands. And behind the scene, as I said Monday, there are always some data sets which are used without that you are aware, and they are pointed by environment variable that are written here for completeness, but you don't, most of cases, you don't need to care. There are examples. Example extended radioactive decay, dedicated. So if you are interested in radioactive decay, I definitely recommend you to have a look to how to use radioactive decay in practice. You can learn a lot if you are interested on that. And now let's move. We have now a few other topics, relatively small, few slides each of them, and independent and separated to each other, but part always to hadronic physics. One is nucleus-nucleus, that some people call ion-ion, but this is the main thing. These are interaction between nuclei. And these are the cross-section and final state which are available in Gen 4. Essentially, there is one cross-section covering both elastic and inelastic. We had several in the past, but then we get rid because this one seems the best to describe the data well. It's based on a Glauber-Gribov parametrization. For the inelastic final state, we have the stream model, FTF, Fritjof, plus pre-compound above 3 GeV per nucleon. Then we have the binary cascade, big model above 6 GeV. Below 6 GeV per nucleon. So again, you see this transition region between 3 and 6 GeV per nucleon, as we encountered already. Then we have another intranuclear cascade model called Liège, INCL, which is used below 3 GeV per nucleon, but not for all nuclei, only for nuclei with mass number below 18. And then there is a different model, quite different, QMD, quantum molecular dynamic model, which is used between 100 MeV per nucleon and 10 GeV per nucleon. This is used on the shielding physics list. And recently, in 11.2, there is a variant of this QMD model, which is specific for low energy, in this range, 3,500 MeV per nucleon, and light projectile and target for medical application, essentially. Carbon ion, essentially, hadron therapy. And then there is ParticleHP for proton, deuteron, tritium, alpha 3, and alpha, below 200 MeV per nucleon for light nuclei. And then there is an elastic final state model, which is this nuclear diffuse elastic covering all energy. These are the physics constructors, so how to use these models, basically. These are the set, each of them using some of the models that I just explained. Ion physics, which is used in most of the case, uses FTF and binary. Then there is the ion INCL, which use FTF, INCL, and binary. The QMD, which use FTF, QMD, and binary. And then we have the PHP, where it's using this PHP, this ParticleHP, beside FTF and BIC. And finally, also this ioelastic physics, which is used in those physics lists. So in most physics lists, is this G4 ion physics constructor, which is used, which is based on Fritjof and binary. And most of the physics lists do not have ion elastic, okay, with this exception, shielding, QBBC, and QGSP BIC. And the shielding is the only reference physics list where the QMD model is used. And there is also this possibility of this light ion QMD that you can use. And then there is this QGSP big all HP, which is the only one using this ion physics PHP way to handle the interaction. So different option. In most cases, as I said, is this Fritjof and binary, which is mostly used unless you have specific detailed reason to pick up a different choice. Now, we change the topic. We go now to gamma nuclear and lepton nuclear interactions. Currently in Gen 4, essentially, we have the same approach to gamma nuclear interaction for all physics lists. So a question that we often get is, I try different physics lists, but I see the same results everywhere. Yes, it's true, because we have only one possibility, so which is used for gamma nuclear everywhere, basically. However, there is an ongoing development, not yet ready, so not yet available, unfortunately, to provide an alternative approach to this gamma nuclear interaction. So for the cross-section, for all energies, we are using a parameterization of experimental data by Mikhail Kosov. Below 140 MeV, which is covering the important resonance region, which is called giant dipole region, we use an extended collection of data, photonuclear data from IAEA. And there is also another option below 20 MeV. There is a so-called land gamma cross-section, which are cross-section coming from Livermore. And for the final state, above 3 GeV, we are using the QGSP, the quark-gluon string model, plus the pre-compound excitation. Between roughly 200 MeV and 6 GeV, we use the Bertini intranuclear cascade model. And below 200 MeV, we have this pre-compound excitation model way to treat, which also take into account this giant dipole region with this photonuclear data. And optionally, there is also this Livermore approach only below 20 MeV and only when the data is available. It's not covering all the possible. Whenever there is no data for a particular isotope, for instance, then the Bertini model is used. For charged lepton nuclear interaction, so electron nuclear, positron nuclear, muon, positive muon and negative muon nuclear, again, currently, we offer only one approach, so it's the same for all physics lists, but we are working on an alternative approach, like for the gamma nuclear, and trying also to cover the tau nuclear. So currently, there is no tau nuclear interaction in Gen 4, but we are trying to close that hole. We are using, for electron-positron nuclear collision, parameterization of experimental data by Mikhail Kosov. And for muon nuclear, we are using Kukulin theoretical computation. And for final state model, the approach is based on so-called equivalent photon approximation, whereas the alternative that I mentioned here that we are working on is based on PDF, on particle density function at the level of nuclei, not at the level of single proton, like the one which are using in heaven generator, for instance. Yeah, so the approach is based on this photon, which means that first a virtual gamma is produced, and then via parameterization, it is converted to a real gamma, and then this real gamma then interacts with the target nucleus. And below 10 GeV, we are using Bertini, and above 10 GeV, we are using Fritjof plus pre-compound, where essentially, given that Fritjof doesn't deal with gamma directly, we make a trick, we convert the gamma to an equivalent with the same energy, total energy, neutral pion, and then Fritjof handle this neutral pion thing. Finally, for neutrino, nuclear interaction. So most of the neutrino experiments are actually using an external package called GENI, which is then interfaced to Geon4 for neutrino experiment, etc. And by default, there are no neutrino nuclear processes in Geon4. However, recently, starting with 11.2, we have introduced the possibility to, via UI command, to activate electron, neutrino, mu, neutrino, and tau neutrino interaction, charge and neutral interaction, and on top of any physics list, essentially. They are also included the neutrino oscillation in vacuum, not yet in matter. We are working on that. And finally, I think this is the last topic, stopping physics. This is a slide that I have already shown you Monday. So, as I said, when negatively charged hadron, like pi minus, k minus, antiproton, and so on, they are at rest, means with zero kinetic energy, something which happens in Geon4 simulation, not in real life, but in real life they get very close, but not zero. In Geon4 they get exactly to zero. There is the possibility to have this process called nuclear capture at rest, which means essentially that these negatively charged hadrons are sucked by the nucleus in some sense. And as I said, for these processes at rest, there is no, the concept of cross-section is no longer applicable. We are talking about lifetime of that process. And the competition is eventually for those which are unstable, like pi minus, k minus, not antiproton, for instance, which is stable, they compete in a Monte Carlo sense with the decay process. So, let's say we have different treatment of the stopping physics, but let's say is somehow similar for most reference physics lists. And most of them are based essentially on FTF and Bertini. The exception where the treatment is slightly different is for the FTF BIC and QGS BIC physics list. You see that the P is missing because instead of the coupling of the string model Fritjof or QGS is not made with the pre-compound, the excitation, the P that you have seen several times, but this time with intranuclear cascade, the binary intranuclear cascade. Moreover, in the case of the INCL physics list, for instance, if you take FTFP, INCL XX or QGSP, INCL XX, which are physics lists based on the INCL intranuclear cascade model, INCL is used for the antiproton annihilation at rest. And this was triggered by interest request from the antiproton physics at low energy, which is here at CERN, happening at CERN. There's also astroparticle experiment balloons, for instance, sent in the atmosphere that are looking for annihilation of antimatter, in particular antiproton, antideuteron, and so on, as a signature of dark matter. So it's important, and they use Geon4 for their detector simulation, for their background evaluation. So they wanted to have a more detailed description of antiproton annihilation, which by default will be handled by the string model, FTF. But of course, we expect that INCL will do a better job because the energy is low. So the intranuclear cascade is more appropriate for an accurate things. We have also a simple treatment of the electromagnetic cascade because what is happening when these negatively charged hadrons are captured is that they are captured as a kind of, they replace an electron in one of the external electron orbital shells, and then they have a sequence of steps where they get to the nucleus. And there, of course, there will be a nuclear interaction. So given this way to fall back in steps, somehow they perturb, they excite the atomic shell, electron shell structure, and there will be some emission of typically X-rays and some Auger electrons following this capture. And the description is quite rough. Essentially, following some data based on muon capture. So there is an ongoing work to try to extend to be more accurate in the case of antiproton captured, for instance. So this is what we are doing. As I said, I repeated more. So Bertini will be used for the nuclear capture of mu minus, pi minus, k minus, sigma minus, xi minus, and omega minus. And frequency of the string model is used for antiproton, anti-sigma plus, anti-xi plus, anti-deuterium, anti-tritium, anti-helium 3, anti-alpha. And as I said, we expect that we are really at the limit of applicability of a string model for the annihilation. And we expect that the INCL, the internuclear cascade, will do better actually than what the string can offer. And that's it. So I have here a couple of exercises for you to in the case that you are interested on radioactive decay and also on neutron HP to try out. I will not go through. I will let you look if you are interested and so on. So I think I can stop here and go for questions and comments.
Thank you, Alberto. I see one question from a few minutes ago. Maybe you can go back to the slides where you had the UI commands for radioactive. It says, can you explain the concept of set threshold for very long decay time? Does it simply turn off all decays having half-lives longer than the threshold?
Yes. This was, so it is not mentioned actually in the slides. So it was introduced relatively recently, a few years ago, because we realized that if you take a calorimeter, you will see, you know, some difference between physics lists that we could not understand where they are coming from. And we realized that the difference were due to very long decays, radioactive decays that were actually happening, you know, with scale of millions of years and so on, that in practice you will not see. So we have put, you know, a kind of cut that by default that we change over the time. I don't remember the current threshold. I think it's 1 year, if I remember correctly. So it is a way to avoid that in typical high energy application where you don't need this, you know, you have a very narrow time window and you are not interested to this effect coming from very long radioactive decay to have an impact. But if you are doing really pure radioactive decay studies and you want to include also those very long decays, then there is a way, a suggested way in the manual, for instance, where you set as a threshold, you know, very high number, and in this way you get rid of this threshold. I forgot to add. I should add to the slide as well. I forgot to put.
Okay, we have a local question.
Thank you. So I'm interested in ion-ion interactions,
yes,
and especially focusing on heavy ion fragmentation. And my question is that what is the difference between the quantum molecular dynamic model and the light ion invariant of QMD?
So the original model, this QMD, was based on a Japanese version which is called JQMD, and it was mostly made for shielding applications. So typically heavy material, tungsten, lead, and so on. This new variant, they actually rewrite some of the key classes actually, and the focus was actually for lighter material like carbon, water, things which are more typical for the medical physics. And also the tuning of the parameter was made for that case. So light target and light also beam in view of essentially hadron therapy thing. So there isn't nothing strongly different, but is a slightly different implementation and focus with tune and validation restricted for a medical application, let's say. And one question that we asked actually to the people that developed was if they think that if they go to heavy material in the, let's say, shielding application domain, if they expect that this new class can do a good job there as well. And they said that they have no idea because they only looked at the medical physics range, so lower energy range and light thing. But he said that in principle, we should try and see. So it's still an open question whether these variants can do a better job actually of the first implementation, also for application relevant for iron, for instance.
Okay,
so I would invite you to try both, I would say.
Okay, and related to this, if someone has a heavy ion projectile, for example, lead,
yes,
in a test beam, and light material as a beam degrader, for example, electronics test beam, then what would be the best final state model to use, QMD or
which energy? Depends on the energy. Which energy?
1 GeV per nucleon.
GeV per nucleon. Very likely should be QMD, very likely. But yeah. Sometimes you can try to use but even ourselves inside Gen4, sometimes we use inverse kinematics when you have a heavy. The normal assumption is that the projectile is relatively light with respect to the target nucleus, but sometimes, as you said, it's the opposite. So this reverse kinematics is automatically used in some of the models. So there is also that thing to.
Thank you.
You're welcome.
There's no additional question on the Matomos, but maybe I'll interject. Currently, there's no configuration which combines light ion QMD and the original QMD by selecting things.
Yes. Yeah, there is just it's not written in this slide. In the shielding physics list, if you use the shielding physics list without specifying anything, you use the original QMD. If you specify in the constructor true, you put the argument true, then you use this light QMD thing. So at the moment, you use one or the other, and there is this possibility when you call shielding to specify whether it's the original QMD or this light QMD thing. And by the way, there is a third option in third variant of this QMD, which is under, it will not be in 11.4, probably will be in 1 year time, which is based on relativistic mean field approach. And also that is made for medical physics application in mind, but could be also useful for shielding, let's say, application.
Okay. Thank you very much.